Hello and welcome to video lesson number 4 on shear strain. Our learning objectives for this lesson are to define shear strain and to explain its units, and to calculate normal and shear strains for deformed bodies that have undergone some kind of general deformation. So what I will ask you to read for this in correspondence with this lesson is Beer and Johnston, section 2.7. So let's define shear strain. So shear strain is an angle that a rectangular shape would undergo when that shape is acted upon by some kind of shearing stress. Now, shearing stress would cause a pure angular distortion of the rectangular shape. And we would start, of course, with the rectangles. And we would end up with a parallelogram. And the angle here at the side of the parallelogram that was vertical makes with the vertical is what we call the shear strain. So it's a change in the angle of the rectangle as we go from rectangular to a parallelogram. So shear strain is an angle. It's this angle that we have shown as gamma, and it's measured in radians. It's worth noting that a radian is not a fundamental unit of length, so shear strain is unitless, just as normal strain is unitless. So for small gamma, it is worth noting that gamma is equal to tangent of gamma, which is also equal to this distance x divided by this distance y. Well, let's consider a fairly straightforward case. So let's find the shear strain for this solid body. I've got rigid plates on the top and bottom, and I've got an elastomeric substance in the middle. So let's find the shear strain that these shearing stresses have induced. Once again, we don't know exactly what the shearing stresses are. We don't know any material properties of the elastomer. All we know is the original configuration of this sandwich was vertical, and we know that it's deformed into a parallelogram. And we know how much the end has displaced. So if we want the shear strain, it's this angle gamma. So gamma would be equal approximately to tangent gamma. So gamma is, which is equal to the displacement of 2 millimeters over the length of 10 centimeters, which is what we have here. And that gives us a shear strain of 0.02. Now we can talk about a more general problem. And let's consider the case of this rectangular shape, A, B, C, D. So what we want to do is we want to find epsilon xx, epsilon yy, and gamma xy for the body below, gamma xy being the shear strain in the xy plane. So we need to indicate that this is x and that this is y. So we're in the xy plane, and gamma xy would be the shear strain in the xy plane. Now let's talk about the normal strains first. So epsilon xx, we're going to do that the same way we always have. It's going to be the length of this red dashed line between A prime and D prime divided by the length of AD. Now for small deformations, for small angles like this, where we've got an angle here and where we've got an angle here, the vertical change of 0.002 is not going to be a significant change. So small deformations, we just need to take a look at the x-coordinate of point A and A prime and the horizontal and the x-coordinate of D and D prime to get epsilon xx. So when I take a look at the length of A prime D prime, I'm going to take that as 1.002, and the original length I'm going to take that as 1. So epsilon xx is 1.002 minus 1 divided by 1, so that is 0.002. Epsilon yy, same story. We know that we're looking at the difference in y coordinates to get the length in the vertical direction. So this was originally 1 unit. The lateral translation does not provide any significant lengthening to the dashed line A prime, B prime. So B prime moving slightly to the right does not change the length of the line. So we would have a final length of 1.002. So that gives us a strain in the y direction of 1.002 minus 1 divided by 1, or 0.002. Now for the shear strain, I'm interested in the change of this angle, of the change of angle A to the angle A prime. How much did this angle shrink? So I'm going to add this angle, BAB prime, to the angle DAD prime, and I'm going to get that result as the shear strain. So the shear strain is angle BAB prime plus DAD prime. BAB prime, well, that's equal to the tangent. So that would be 0.002 divided by the original length of 1 plus 0.002 divided by the original length of 1 for a shear strain of 0.004. So that gives us a way of computing normal and shear strains for a two-dimensional solid or a higher dimensional problem, 2D or 3D problem. And that is all for video lesson 4.